Your agent does not need 100 tool schemas in context. Route first, then load only the chosen tool. You feel your assistant slowing down as you add more capabilities. You see long load times and brittle prompts. Today, you will learn a pattern that keeps latency low and tool usage precise. By the end, you will understand how to route to the right tool using tiny metadata and only load the heavy code when you decide to run it. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced with simple, concepts-first Python that helps you solve bigger, real-world problems. We will build a tiny router for a handful of tools like a web search tool, a calculator, and a document summarizer. The router looks at the user text and decides which tool is most likely useful. It does that using light metadata and regular expression token matching. If the router is confident, it dynamically imports and runs only that tool. This keeps memory and startup time down, and it fits nicely into systems that may have many optional tools. This snippet defines lightweight tool metadata for routing without loading schemas. This snippet sets up a small list of tool entries where each entry has a name, a short description, and a few example trigger phrases. The key idea is to keep each entry tiny and textual, so the router can scan them quickly. You will see simple strings that describe what the tool does, and a short list of tokens or patterns that hint when to use it. These items are intentionally inexpensive to construct. They are not full schemas or heavy imports. Later code will use these fields for fast matching and ranking. Next, we will turn those descriptions into scores so we can compare tools. This snippet ranks tools from metadata using Python RE tokenization and sorting. This snippet uses regular expression-based tokenization to break the user text and tool descriptions into simple words and patterns. Regular expression tokenization here means using the Python RE module to find word-like pieces and lowercasing them for comparison. The code builds a simple overlap score by counting how many tokens from a description appear in the user request. It then sorts the tool list by that score in descending order. The important detail is that this ranking is very cheap. It runs in linear time relative to the number of metadata tokens, and you can adjust whether to count unique matches or weighted matches by changing one small aggregation line. Now we pick a single tool if the score is good enough. This snippet selects a tool using repowered matching with a minimum threshold. This snippet looks at the top-ranked tool and verifies its score meets a configured minimum confidence value. The minimum threshold acts like a safety net, so the router does not pick a tool for vague or unrelated queries. The code computes the best score for each tool and then compares that best score to the threshold variable. If the best score is below the threshold, the router returns a fallback or asks for clarification. If it passes, the router returns the tool name and the matched tokens. You can change the threshold number to be more or less conservative. Lower the threshold to accept broader matches and fewer fallbacks. Raise the threshold to avoid false positives at the cost of more clarifying questions. Next, we make the router more cautious for short or ambiguous queries. This snippet adds a guardrail by raising the threshold for ambiguous queries. This snippet inspects properties of the incoming text, such as its length or the number of match tokens, and increases the required confidence if the text is suspiciously short. The idea is simple. Short prompts often lack context and produce accidental matches. So, the code multiplies or replaces the base threshold with a higher value when the query is brief or when multiple tools score similarly. you will see a small conditional that bumps the threshold and then reevaluates the top candidate. This guardrail reduces accidental tool calls and makes the router defer rather than execute when certainty is low. Now, we run the chosen tool, but only load it when needed. This snippet lazily loads and runs only the chosen tool function using re. This snippet takes the confirmed tool name and performs a runtime import or an on-demand lookup to call the tool function. The lazy loading step means the heavy module or remote client is not created until this moment. The code maps the tool name to an import path or to a factory function, and then calls it with the original user text and any match tokens. Using the re-driven match helps pass relevant arguments like a query phrase or numbers. The result is returned to the user. The most important knob here is ensuring the import or initialization is cheap enough for occasional on-demand use, or else you can cache objects after the first call. In a real project, this pattern maps cleanly to services and micro-libraries. The metadata can live in a small JSON or a database entry. The lazy loader can call a remote service client or import a heavier local module. The routing step stays fast, so the system scales to many candidate tools without paying the load cost for each. Recap: it is a routing-first pattern that inspects tiny metadata and uses regular expression token matching to pick one tool. Use it when you have many optional capabilities and you need low latency and low memory. One caveat is that Regex token matching is simple text matching and can miss nuanced intent. So include a fallback or a clarifying step. For one clear next step, tune the confidence threshold and test on a representative set of queries. Measure how often the router picks the correct tool and adjust the threshold to hit the precision recall trade-off you want. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.